Okay, so, all right. So can the claim in this previous exercise be used to compute a certain integral? Now let's notice what this previous exercise says. If you have a surface that's symmetric through a certain plane, the function f has odd symmetry through the plane, then the integral must be 0. Right? So symmetry argument is basically a symmetry argument for this new context of surfaces and scalar line integrals. Okay, well, so what we need to do is we need to decide, does this domain satisfy the requirement? Is it symmetric through some plane? And then secondly, is this function, does that function have odd symmetry through some appropriate plane? So the big question is figure out what is the right plane. Well, that's the first question I'll say. What is the right plane through which to try to apply this this previous result? And then we have to check the two conditions. All right, so now we've got a big hint on that. The hint is a vertical plane that's one of the level sets of f. Here's our function f. So x plus 3y. Let's draw some of its level sets. Colors for other things. So x plus 3y equals various constants. I can see the normal vector, right? 1, 3, 0. So we've got a bunch of planes that look like this, etc. And is our domain, which is a sphere, well, it's a hemisphere, right? It's the top half of that. Is that symmetric through any of those? And I appeal to your geometric intuition. The only reasonable candidate is the one that goes through the origin, right? Okay, so let's think about that one. X plus 3y equals 0. Well, yeah, it is, because spheres are awesome. Right? Spheres are just crazy symmetric. This is a vertical plane. When you reflect through a vertical plane, the reflection is entirely horizontal. So that means that every point on the upper half of the sphere is going to reflect to a point on the other side of the upper half of the sphere. So yeah, the domain is symmetric through that plane. That's our plane. Everybody good? Okay. Now, the annoyance is we've got to check, does the function have odd symmetry, right? And there's different ways to see this. I'm going to show you the most blunt way to do this, and I'm going to explicitly find a formula for this reflection. How do you reflect through x plus 3y equals 0? Now I'm going to make the argument in R2. I'm going to look at this line there, x plus 3y equals 0, because nothing's happening in the z coordinate anyway. We've agreed that the reflection is horizontal. So, all right, given some vector x, what's the formula for the reflection of x? And I've got to know this formula for this reflection because I've got to plug the reflection into the function to see if the function has odd symmetry. Okay. All right, this is not a terribly brutal thing to do. It's just there's a couple of steps that go into this. First thing I'm going to do is figure out a formula for this vector. That formula, let's see, that vector, excuse me, I guess I'll call that, let me call it P temporarily. And I want to write that down because it is going to be convenient for figuring out R. So in particular, R plus X is 2P. If you were to sort of extend, well, I'll do this in yellow. If you were to extend and make a parallelogram where you draw x plus r, geometric appeal, x plus r is equal to 2p. Yeah? All right, so if I can figure out p, I already know what x is, then I can solve for r. So what is this p thing? Okay. Let's see here. Good news. I do know one thing. I know this vector, perpendicular to that line, is this vector I'll call n. That's 1, 3. Yep. Okay. So that means I can write down a vector parallel to the line. Let's see here. Oh, you know what? There's an even easier. Yeah. So I'm going to try to figure out what is this dark blue vector. I can figure out that. Actually, if I figure out that dark blue vector, I kind of don't even really need p, do I? Anyway, let's figure out that dark blue vector. I think that's going to be straightforward because here's and let's call that d, I guess. If I know d, then I can forget about p. I don't need p at all. If I can figure out what d is, r is x minus 2d. How about that? Right? Okay, so what is d? Well, d points in the in direction. I know that the magnitude of d is, magnitude of d is the component of x in the in direction. That's this distance component of x in the in direction. So that tells me that. And by the way, I know how to do this component. This is x dot n divided by the magnitude of n. That's how we compute components. Okay. Now, what do I want to do with that magnitude? Well, I want to take that magnitude and I want to multiply by a unit vector pointing in the in direction. So, which I guess I could call d, or magnitude of d. Right? But that unit vector, n over magnitude of n. That's what I want to do. So the unit vector pointing in the in direction, and that'll give me the d vector. Because this vector here, that vector has magnitude 1 multiplied by magnitude of d. This product now has magnitude equal to what it's supposed to, and it points in the direction of the in vector, which of course so does d. Okay. All right. So taking that and multiplying by that, then I see what I have is d is equal to x dot n over the magnitude of n squared times n. Yeah? How are we doing? Everybody on board? Okay. And we know what the n vector is 1, 3. So this is a little formula that you can use. Now, final step, our reflection. Keep in mind we agreed the reflection vector is x minus 2d. That comes from this picture up here. Reflection is x minus 2d. And so that means it's x minus 2x dot n over magnitude of n, quantity squared times n. Yikes. Okay, is everybody on board? Okay. All right, now, so this is our formula for our reflection. Now, again, the reason we needed that is we needed to look at our function and decide if our function was odd. And let's see, where is our function? Here it is. The function is x plus 3y, which I'm going to rewrite as x dot n. Right? That's x comma y dot the n vector, 1 comma 3. Again, the z-coordinate, nothing happens with the z-coordinate. Okay. All right. So, let me just copy that down here for convenience. F of x is x dot n. And now let's ask the question, is f odd? Well, I've got to compute f of the reflection, and I hope that this will give me negative f of the original point x. And that's all plug and chug at this point. Well, let's see here. Okay, f of the reflection. That's x dot, or excuse me, that's reflection dot n. Right, that's what that tells me. Okay, so my reflection is right there. So x minus 2x dot n over the magnitude of n squared times n. That's what I have to dot with n. Okay. All right. So let's see, what do we get here? Well, the first term I get x dot n. Yeah. Okay. All right. Next, looking at that dot that. Well, you can see this coming. I'm going to have an n dot n. Right. So I have minus 2 x dot n over n squared, and then that n dot n is magnitude of n squared. Very conveniently, those cancel. Now I have x dot n minus 2x dot n, which is negative of x dot n, which is indeed, as required, the negative of f of x. And so the function has odd symmetry. So there's a bunch of, there's a certain amount of details you have to write down. You get, the most of the work you noticed is in going into finding what is the formula for how to compute that reflection, and it's a sort of a bonus exercise from chapter 1, you might say, right? But once you know the reflection, function's got odd symmetry, and we're done. Everybody happy?
Yep.
Okay.
Thank you.
Yeah, no problem.